All right, AP Chem, we're going to continue with the Day 74 VSEPR lesson. I'm going to ask that you do through letter M of these. The rest will be optional. You can do those and work with me in office hours if you want to go over any of them, but the ones that I don't actually do on the video here. Okay, so let's get going with ammonia here. Okay, and nitrogen has 5 valence electrons. Have that. So we're going to do this. Right, so everything has an octet there, and that is the Lewis dot structure for ammonia. Now we're going to go over to the chart. Okay, so we drew our Lewis dot structure. We see that it has three bonding pairs and 1 lone pair, so we write that as an AX3E1. We come over to our chart and we have that right there. So since there's 4 domains, electron domains, it's part of the tetrahedral family, 4 domains, but its actual shape is trigonal planar. So this is not flat, it's shaped like a pyramid. So these 3 legs are pointing downward from the central atom, and then it has the lone pair, and that's what pushes them downward, is that repulsion between this lone pair and the 3 bonding pairs of electrons right there. So that is that. Okay, so now we have 16. We need 18, 2 more, so we're going to put them here. Alright, so now we have 18, but nitrogen still doesn't have a full octet, so what we can do is we don't want to add or subtract any, we just want to move some, so we're going to take this pair and we're going to move it and make a double bond in here. Alright, so you have a molecule with 1 double bond and 1 single bond, and oxygen has an octet, nitrogen has an octet, and oxygen has an octet over there. Again, this would be a resonance structure because the double bond could have been put over here. That would be the same molecule. That's a resonance structure for that. The minus sign means that it's negatively charged. That means there's an extra electron. So you added an extra electron right there. Okay, so how many bonding domains does nitrogen have? It has 1, 2. And then how many electron domains? It has 1, 2, and then the lone pair also is 3. So this is going to be so we come on over here and we find that right there. It's part of the trigonal planar family, but it doesn't have a top molecule to make a trigonal planar, so it's actually a bent molecule. Not exactly the same as water being bent. Different bond angle for this bent molecule than this one, because there's a different number of lone pairs on these 2 molecules. So that's a bent molecule. So domain is the family that it belongs to. And molecular geometry is the actual shape. Okay, so you can see once you kind of get the hang of these take about 2 minutes apiece. Okay, let's keep going. Draw an octet around everybody. Okay, so now we have 8, 10, 12, 14. So we have 2 electrons too many. So the first thing we want to do is we want to erase 2 electrons. So I'll just pick these 2. Could pick any 2 pretty much. So now I have 8, 10, 12. All right, that's good, except this oxygen doesn't have an octet. This one does, but this one doesn't. So what we're going to do, we don't want to add or subtract, we just want to move. So we're going to move these in to form a double bond there. So now both oxygens have an octet. All right, now you say, what would that be here? Well, there's only 2 atoms. This is not a trick question, but you should understand it. There's only 2 atoms. The only way you can have any kind of bending or shape to it is if there's at least 3 atoms involved in the bond. Here there's only 2, so they can't be anything other than a straight line. Okay, so it's just linear. It's not even really part of any of those families. It's just a linear molecule. Okay, it doesn't have an ax notation really. It's just a linear molecule. All right, keep going. So we don't know the geometry, but we know hydrogen can't be inside because it can only have one bond. It can only bond in one direction. So we're going to just draw it as a straight line like that. Okay, so we have 6. We need to use 14. Hydrogen already has full octet, so we're going to go ahead and let's draw octets all the way around the oxygens. Okay, and let's see what we have. We have 8 right there, 10, 12, 14. So that's it. That's complete. Okay, so what you have here is 2 possible sets of 3 atoms. So 1, 2, 3, and then starting on this side, 1, 2, 3. So that means you can have an angle here between these 3 and then a different angle between these 3. So let's do the oxygen on the left. And what that's going to be is an AX2E2. It has 2 bonding domains and 2 lone pair domains, a total of 4 electron domains. That means it's going to be tetrahedral family. I'm going to start abbreviating that just tetra. And if we come down, it has the same shape as water. AX2E2 is bent. So that's going to be tetra and it's going to be bent. Okay, the oxygen on the right is exactly the same except flipped over. It's also, alright, and that's also tetra and bent. Now, how is it bent? That's a little more complicated, but what these 2 are going to want to do is be as far away from each other as possible. So again, it goes to repulsion, and wanting to be as far away from each other as possible. So one way you could draw this would be like this. Okay, whatever gets these 2 as far away from each other as possible. And that's the way you can kind of view what that molecule looks like. Okay, so we'll move on to the next one. Okay, that's drawing it as symmetrically as possible. Now we need to place 14 electrons. And we've done it. We've used all 14 and every one there has an octet. So again, you're going to have a situation where you have 2 different opportunities for this to bend, but between these 2 right here, this one is the carbon on the left, so they both have the same ax notation, both of these carbons. Okay, so that's going to be tetra and tetra. 4 electron domains, and all 4 are bonding domains. Same with this one. Okay, so this is a little bit challenging to show on a piece of paper. Okay, so what we know is this carbon is going to have a tetrahedral shape. That means that 3 of these of these four are going to be kind of sticking down like this, and one of them is going to be sticking up. So again, it's a three-dimensional structure. It's like three legs on a stool, and then one of them is going to be sticking up. So we can say that this hydrogen is the one sticking up, and these three are sticking down. Now for this carbon, it's the same thing. Again, it's hard to picture this in 2 dimensions, but this one is this carbon is one of the legs of this carbon, and you can think of this carbon as one of the legs of this carbon, so it's going to do the same thing. What you know is this hydrogen is going to probably point in the opposite direction of this one. If this one's pointing up, this one's going to be pointing down. Again, that's the best I can do with this without being able to have a model for you as I would have in the classroom. So that's going to be your answer for that. All right, go ahead and do this. Okay, so I've used 2, 4, 6, 8, 10. I need 2 more. Hydrogen can't hold anymore. And both of these carbons still need an octet, so those are logically, those last 2 are going to go in the middle to make a double bond. So carbons both have an octet, the hydrogens have an octet. Okay, so now we again look at each carbon separately. So this is kind of a central molecule, this is a central molecule. So what you have here is 1, 2, 3 electron domains, and all 3 of them are bonding, so there's no lone pair. So this is going to be for the carbon on the left. Okay, it's an AX3E0. All right, we come over here, we'll find that, and there it is. It's trigonal planar. Okay, so it's a flat triangle. There's no third dimension to that. It's just laying flat on the table like that. Okay. So, but we see it, they come off as angles. So that means, let's go ahead and do the other carbon first, and then we'll draw it. It's also same thing. Okay, so this is trig planar, and that's both the domain, in other words the family, and it's also the specific shape of this. When there's no lone pairs, then the family name and the molecular name are the same, okay? And this one I'm going to put ditto ditto. It's the same over there. Okay, so what this is going to look like is a C with a couple of H's going off like that. It's a double bond, so we put that, and then C. So that's trigonal planar. Three electron domains, 3 bonding domains. Now this is going to have the same thing, except we're going to draw these as dashes, because this one, if these are flat on the paper, if they're parallel to the paper that I'm writing on, these 3 right here, these 2, one of them is coming out at you, and the way to really draw that with perspective model is like this, and I should color that in. This one's coming out of the page directly at you, and this one's going back away from you. If I draw this properly, they would both be on the same plane going this way, in and out of the page. You wouldn't even be able to see both of them, because one would be behind the other. So this is going up and down on the page. This one's going back and forth like that. But that's the best we can do to draw it. This one's coming out at you, this one's going away from you. Again, these want to spread out as much as possible, and so that's how they would do that. All right, let's keep going. Okay, when we were doing covalent bonds and doing this a couple months ago, we did play around with nitrogen being the central atom, but it's not, and we don't want to get into formal charge at this point. And so we know that this is the configuration, so we're going to go with that. Okay, there we go. So we've used our 10 electrons, but carbon doesn't have a octet, and we don't want to take any off or put any more on because we have the right number of electrons, so we have to rearrange. Well, we can't move this, that's stuck. So it's got to be some of these lone pairs out there to give carbon the octet. So it needs 2 more pairs or 4 more electrons. I'm just going to erase that to create a little more space. So now we have a pair, and a pair. Okay, there you go. So it's a triple bond right there. So hydrogen, carbon, nitrogen. So everyone has an octet. Everybody's happy. Okay, how many electron domains does a central atom have? It has 1, 2. Whether it's single, double, or triple bond, that's still 1 electron domain, and it's a bonding domain because it's creating a bond. So is that. So this is going to be it's AX2E0. And if we come over here to our sheet, we see that that is a linear molecule. It's a straight line molecule. So it's part of the linear family, and its actual shape is linear. Okay, and so this is actually an accurate representation. If you want to draw it again, you can do that. Okay, and that's a straight linear molecule. All right, let's move on. So go to your periodic table and find silicon. And silicon has 4 valence electrons. It's right below carbon. So this is our symmetrical starting representation right here. Okay, fill everything with octets around the outside. Okay, there we go. So that's 8, 8, 8, 8, 8. That's 32. So everyone has an octet, and we've used all 32. So that's the representation. So you can see that for the central atom, it has 4 bonding pairs, 4 electron domains in all, and 4 bonding pairs. That's an AX4E0. So that's going to be tetrahedral. So both the family, the domain, and the actual shape is tetrahedral. It's going to form, it's going to look exactly, have exactly the shape of a methane molecule, look like that. So that's going to be tetra. Okay. And that's it. We really can't draw that, but as it's 3-dimensional, but that's what it's going to look like. So one of these is sticking up, and the other 3 are like the legs of the stool, and the silicon is right in the middle. Okay, and go ahead and place your octets. All right, so we have 24, 8, 8, 8, and we need 2 more, and phosphorus needs an octet, so we just put it there. And there we go. So this is going to be 4 bonding domains, 4 electron domains. 3 of them are bonding, and 1 of them is a lone pair. Again, you're only interested in electrons around the central atom. That's what determines the shape of the molecule. Okay, come back to our sheet. And there it is, AX3E. It's a part of the tetrahedral family because it has 4 electron domains, but it's trigonal pyramidal. So it looks, this is a better view of it than this. It's kind of like a pyramid. It's a 3-sided pyramid. Okay, so that's what that's going to be. That's because this lone pair is pushing these electrons in these bonds down. It's creating an angle in those. Okay, if these electrons weren't there, it would be flat. It would be a trigonal planar. But they are, so they push these bond angles, these legs down, and you have a pyramid shape. So that's going to be tetra. That's the family because it's 4 electron domains in all. 3 of them are bonding, 1 lone pair, so that's trigonal planar. Okay, we'll move on. CS2. Okay, so you have 16 in all, so We're going to just assume it looks like this. Alright, so we have 16, 16, so we don't want to add or subtract any, but carbon does need its octet, so I think we all know how to do that by now. We're going to take those, put them in here. Alright, so the shape is determined. Carbon has two electron domains, and both are bonding. And no lone pairs. So we come back to here, AX2E0, that's just going to be a straight line, a linear molecule. Okay, so and we should write that. It's both in the linear family, and it is in fact linear. Okay, next up. Okay, we may not be sure which is the central atom. We know it can't be hydrogen. It's either oxygen or bromine. But we're going to just assume it's, again, we're not going to get into formal charge to figure that out. We're just going to assume it's the oxygen. We actually did this one before, so. Okay, so we have 10. We need 4 more electrons, so we're going to put them here. And now we have 14 electrons, and all atoms have an octet. So the angle is going to be formed by the central atom. So it has 4 electron domains. That makes it part of the tetrahedral family. 2 of them are bonding, 2 of them are lone pair. Okay, so come back to the chart. And there it is, tetrahedral, bent just like a water molecule. So if we come over here and draw that, it's going to look like this. And then we can complete it by drawing those lone pair up here. So they're not directly on opposite sides. This is just our initial representation to draw the molecule. If they were on exactly opposite sides, this would be a linear molecule. But they're not. They're in the tetrahedral formation, so they're taking the place of one of these and one of these. That means they're kind of on one side, and these two are kind of on the other side. And again, like a water molecule, that's the shape that it has right there. All right, one more. I actually want to do 2 more. Okay, so we're going to do this one. Okay, so it's xenon. Excuse me, xenon difluoride. I'm going to draw it like this. Okay, and so we have 16 and 16, but we need 22. Okay, so where do we put those? We can't create any double bonds here because fluorine's got a full. So we're going to put them here and here. So now xenon has an octet, everybody has an octet, but we still have 2 more electrons. That's 8, 8 is 16, 18, 20. So where do they go? They go on xenon as another lone pair. Remember, xenon, this is an example of an extended octet. Okay, so xenon can have an extended, so it actually has 10 electrons, okay? So that would be A, X, E. So xenon has 2 bonding domains and 3 lone pair domains. So now we have to go to the other side of that sheet, and if we look on here, there's 5 electron domains around xenon. So that would be part of the family, this family over here of trigonal bipyramidal. However, it doesn't show this one on a sheet, so you kind of have to think about what it would look like here. So this is if all 5 of those electron domains are bonding. It creates a trigonal bipyramidal. In other words, it's 2 pyramids. a three-sided pyramid on the top and then one on the bottom that's upside down, if you kind of imagine those, all those having faces on them. So that's an AX5E0. Then what you do is you take one of these equatorial, these three are called equatorial, they go around the equator of this, and if you do that and then turn it on its side, you have two of the equatorial left. These are the axial. These are these two right here. They've turned this on its side, and you have one lone pair. Now, if you take off two of these equatorial, so it's always the equatorial that get taken off first, then what you have is you have two lone pairs. There's the remaining equatorial right there, and there's the axial. Again, these two are these two right here. They just turned the molecule again on its side. So that's a T shape, but it's not a perfect T. It's bent down because these electrons are pushing down on these electrons, and they're making the angle look more like this. Okay, but that's not even what we're talking about. We're talking about one that's AX2E3. So you're taking off this one now. So now you have three lone pair electrons around this central atom and two bonding. What that's going to do is it's going to straighten the molecule out back again. It's going to be linear. Okay, so that one wasn't included on this sheet. You almost never come across it, but so it's going to be linear. This is going to be gone. There's going to be a lone pair right here, and they're going to be equidistant from each other around the central atom. So they're going to basically cancel each other out. So this is going to be a linear molecule. So it's part of the trigonal bipyramidal family, but it's linear. Okay, and that's the end of that down to M. I do want to do one more, but what I did, I forgot to put the hybridizations in for all of these. So let's go do it. We can do it very quickly from the sheet here. So let's go back to D, the second one we did, NH3. It's AX3E1. So you simply come over here. And anything that's in the trigonal bipyramidal family is going to be an sp2. So the s orbital is in this. So the s orbital and two of the p orbitals, that px and the py, are going to merge together to form three sp2 orbitals. Again, remember what that means. It means s, p, p, and you end up with three of these. So you end up with an spp, an spp, and an SPP, or three SP2s, okay? Three of those. All right, so that's the answer to that one. How about this, AX2E1? So we come here, right there. So that is also part of the trigonal bipyramidal. It has three electron domains, and so therefore it's also sp2. So the family, not the actual molecular geometry, but the family determines what the hybridization is. Okay, this hybridization is none. It's just it doesn't hybridize. It's just a diatomic molecule. Okay, this one right here is part of the tetrahedral family. So that's going to make it an sp3. So this is an sp3 bond with this oxygen. This is an sp3 bond with or lone pair, but it's still an sp3 configuration. This is an sp3 and this is an sp3. You have four sp3s. S, P, P, P. That's four. So you end up with four equal bonds. And the same would be true for this oxygen over here. Okay, this one is also tetrahedral. It's also sp3. Again, all you have to do is see what family is it in, and all of these are sp3s right here. Because 4, 4, 4 is sp3, 3, 3, 3 is sp2, and that's how you do it. It's not hard. All right, let's keep going. Okay, so this is an AX3E0 right there. So that's part of the trigonal planar. So that's sp2 hybridization. So an s and two p orbitals. I'll write it up here. Okay, this one is going to be AX2E0. So we come over here again, right there, and it's an SP. It's part of the linear, so it's just an S and the PX. So I'll write that here. Okay, this is tetrahedral. That's SP3. Tetrahedral family. It's the family, not the specific shape, that determines the hybridization. It's SP3. Okay, linear. That's AX2. So that's SP. Okay, this one is tetra. That's going to be SP3. And the family for this one is trigonal biplanar. So that's going to be, that's 5 electron domains. So that's going to be SP3D. In other words, xenon has 5 electrons. That means it has an octet plus 2. That's an extended octet. So it has to have some place to put those 2. So it puts them in the d orbital. It's like its storage locker for those extra electrons. So that's an SP3D. Okay, I think I am going to leave it at that. I just wanted to be sure I had an example of an extended octet there. You're not tested on extended octets. So you still have another page of this. I'll leave this for you to do and practice on. Maybe I'll put these answers up, or you can just come see me in office hours. That'll be a good excuse for you to come see me, because I like to see some of you and I don't ever get to see many of you. Okay, so you can do those for extra credit, or not extra credit. It's not extra credit. Just do them if you want to practice. Okay, so thank you, and we will see you on the next video.